Hi, this is the third video of the series of videos that I'm going to explain about quantum computing. In this video, I'm going to talk about quantum gates. What is a quantum gate? A quantum gate is a linear map between Hilbert spaces. There are two terms that I need to clarify here. So what is a linear map? It is a map between two vector spaces. It requires some special property that if you have a linear combination of two vectors in the domain space, then it becomes a linear combination of the image vectors of the codomain spaces. And what is a Hilbert space? A Hilbert space is a vector space of all qubits. The easiest way to exemplify a Hilbert space is to think about quantum state of a single qubit. And not just a Hilbert space is a vector space, there is an inner product defined between every quantum state. So if you take 0ket and its dual vector, which is bra 0, then the inner product are denoted as this one, and denoted is the inner product notation. So 0 bra inner product with 0ket equals to 1ket, 1 bra inner product to 1. But if you have opposite digit, then the inner product is 0. So anyway, let's see some examples of quantum gates. X gate is that it interchanges ket 0 state and ket 1 state. So if you act X gate on ket 0, you get ket 1. And if you act X on ket 1, you get ket 0. Another example is Z gate. So unlike X gate, Z gate do not change ket 0. Makes ket 1 stays at ket 1 state, but it changes its sign. Another example is H gate called Hadamard gate, and Hadamard gate changes ket 0 and ket 1 into combinations of ket 0 and ket 1 as follows. So these XZH gates are 1 qubit gate. There are 2 qubit gates too. The typical example of 2 qubit gate is controlled NOT gate, denoted as CX gate. C means the control qubit, which means that the qubit I is the control qubit, and qubit J is the target qubit. So we act X gate to the target qubit, in this case qubit J, when the control qubit, in this case qubit I, is 1. So there are 4 states that we can act this controlled NOT gate here. Let's say C0x1 acting on 0, 0 is equal to 0, 0. Why? Because the qubit 0 is at the ket 0 state, so we don't act X gate on the qubit 1. However, if you act the same controlled NOT gate to 0, 1 ket, then since the target qubit, which is qubit 0, is at the ket 1 state, you activate X gate and act on qubit 1. So the 0 ket becomes 1 ket. So the overall 2 qubit state turns into 1, 1 ket. The rest of the qubit state are easily computed. How do we represent a quantum gate? A quantum gate can be represented by a square matrix. For example, if you take X gate, it simply interchanges ket 0 and ket 1, so you can make off-diagonal entries 1 and diagonal entries 0 2 by 2 matrix. And the Z and H gates are also represented as the following 2 by 2 matrices. So this matrix representation of quantum gates gives you nice matrix multiplication which implements the actual action of quantum gates to every quantum state. So let me give an example. Let's say we act X on ket 0. I can rewrite into matrix multiplication by substituting X with 2 by 2 matrix and ket 0 as 2 by 1 matrix. So I get 2 by 2 matrix times 2 by 1 matrix becomes another 2 by 1 matrix, in this case 0, 1, and 0, 1 is equivalent to ket 1 state. So therefore I retrieve the same result as if I act my X gate to ket 0. So the matrix multiplication of the representation of quantum gate gives a nice way to compute our quantum state in matrix multiplication. So in this video, we briefly looked over what is the quantum gate, and in the next video, we're going to talk about actual quantum algorithm. Thank you.